Welcome back to our 1-bit full adder part 2, and in this segment we're going to take the circuit that we built in our previous video, our 1-bit full adder, which we derived from a truth table all the way to the box right here. And if you haven't looked at it, go back and review it before you actually look at this one. And we're going to go into Logisim, and we're actually going to build that. Now this is what we want to actually construct right here, and this is taken from our textbook, our computer organization and design, the 5th edition by David Patterson and John Hennessy. And excuse me, here is our box down here. This is our 1-bit full adder, and we're going to incorporate this operation to an AND and an OR on A and B. We're also going to add to that an A invert and B invert, which will turn these into NOR and NAND gates specifically, and then choose the operation. So we're actually going to build this in Logisim, and this can be used to produce a 2, 4, 8, 16, 32-bit adder by just incorporating this. We're going to build this. So let's pull it over to the side. And to do this, we're going to actually add a circuit, and we're going to call this a 1-bit ALU. So we'll go in here and do that. Well, now let's bring our image back over. We want this the adder, an OR gate, and an AND gate. So let's take this over here. So we'll go into our arithmetic, and we'll bring in an adder, and we'll make it a 1-bit adder. Put that right there. We'll go into our gates and put in a OR gate right above it, and it will be 2 inputs, not 1, not 5. And then we'll put an AND gate up here, and likewise it will be 2. Move it over a little bit. Here we go. Then we'll put a multiplexer, and that multiplexer is this oblong thing to the right here. We're going to have 3. We're not going to use all the bits. It's a 2-bit operation. So we'll take our plexers, multiplexer over here, and it is a 2-bit selector bits with a 1-bit output. And we're going to change this so the selectors are on the top. So there's the selector bit right there. So the AND comes in as 0, 0. The OR move up a little bit, comes in there. Actually, move it up just a little bit. There we go. Comes in here, and then the AND, the adder, the results come in right there. And we don't use the 4th input selector right there. We'll go ahead and add our operation, and this is we've got these 3 things in here, and let's add our operations right now, which is up at the top. It's a 2-bit selector, so we'll go into pins. We'll make it face south. It is 2 bits, and we'll call it operation, and we'll put the label on the north, and then we'll go up here, and the operation will come down right there. Let's go ahead and do the carry in. And we'll pull our diagram over here. You'll see the carry in up there. That's a carry in. That's a pin. Like this one, it faces south. Okay, it is a 1-bit. Okay, and the operation, instead of saying operation, it will be called carry in. And there is carry in. Very good. Now, so what we've got left, we'll pull the diagram back over. We've got the get A and B in there, and we'll do the carry out. So here's carry out. Pin, it's actually facing north. It is 1 bit. south, and the label is carry out. Okay, now the inputs. We'll do B first, and what we want is we want to reproduce this down here. We want B coming into a multiplexer that allows us to pick either the B or the negation of B into both the adder, the OR gate, and the AND gate. So let's get our plexer first. Let's get a plexer, a multiplexer, and we'll put it right here. So there's our plexer, and we'll line it up so the results comes right to the input there. We'll also make it go up to the OR gate and the AND gate. Okay, let's finish up the input here. We'll go get a pen, and we're going to make this B. It's a single bit. B, and then the label is east or west, excuse me. Face it the right way. There we go. And now we got to put a NOT gate right here to negate it. There we go. So that finishes it up. Let's move it in a little bit. There we go. And let's copy it. I'm going to do a Control C on a PC. It's a Command C on a Mac, by the way, and Command V or Control C or Control V, excuse me. And now we're going to do the same thing with A. Put it up here, and we will change that to A input. A. And have that go into the top of the AND gate and the other parts, the OR gate and the adder. The only two things we have left to do is to put the A invert and B invert. And let's go ahead and do the muxes. We'll change that so the selector goes on the top. We like that best. And we'll do B invert. Put right that there. We'll face it south is a single bit. We will call it B invert, and that will tell it to either take B or B negation. Move this over just a little bit and come down here. Boom. And now we're going to copy that, and this will be A invert. Okay. Oops. B invert. We'll change that to A. Got a little confused right there. Here's A invert, and it'll come down here to this one. Alright, so there we have our arithmetic logic unit. Let's go ahead and produce our results right here. I'll take a pen. It will face it west, single bit output. It is output, and the label is results, and the label location is east. There we go. So there is our 1-bit arithmetic logic unit. We can test this out, a quick test of it. Will reveal whether it actually works or not. We'll turn this on. The carry in will be 0. The operation will be, we'll do an add. B invert and A invert is off, so we'll add 1 and 1, and that should be a result of 0 with a carry out of 1, and oh, that's got to be output, excuse me. Make that output. Alright, there we go. Now let's test it. Alright, so that's output. Let's add 1 and 0. Should be 1 with no carry. And 0 and 0 should be 0 with no carry. That's really good. Let's try the AND gate. A and B1, so that's operation of 0, 0. That's run. Let's do 1 and 0. That's 0. Let's do the OR gate. And that's 1 right there. So everything looks like it works pretty well. Alright, now, one last thing. Now that we've got this working, let's go to our main circuit. And now let's say we want a 2, 4, 8, or 16-bit adder. Well, we can take our 1-bit ALU and put it right there. And now here we have it. We have A and B inputs. We have carryouts. We have the results. So what I can do is I can just add bunches of these. Oops. In a row. That's yours 2 right there. Line them up. Alright, now I have 4 bits coming in, each one to its respective arithmetic logic unit, 4 results coming out. The carry in of 1, the carry out of 1 is carry out to the next one. Oh, excuse me, that's operation. There's a carry out. So carry out of 1 is a carry in of the next one. And there's carry out right there.